Streaming potential is different from the ones we've studied. Streaming potential is different from electroosmosis and electrophoresis in that rather than applying a potential is going to be the result. So imagine a capillary that is going to connect two fluid reservoirs. So we have two fluid reservoirs and we have pistons that are movable. So imagine we have a piston here and a piston here separating the piston allows us to apply a force and increase the pressure on our solution. So imagine we move this piston in and generate a high pressure on this side, and this piston moves out. So there's a lower pressure on this side. So we have a pressure drop across this capillary, which once again is not drawn to scale. We're going to draw it a lot wider than it really would be. Okay, imagine we had a surface potential on this capillary that was positive. We know that it's going to attract co-ions that are, we know it's going to attract counter-ions and repel co-ions, so we end up with an excess of counter-ions in this capillary space. And now we're going to apply a pressure here, a pressure that's higher on this side than that side, so we have this pressure drop. And of course, if we apply a pressure like that, that's going to induce flow through the tube. So in this case, the flow is being caused just by a pressure difference. When the liquid is being pushed through here, it's going to drag the ions with it. So this is sort of the flip side of electroosmosis. Instead of moving ions dragging the fluid's going to be dragging the ions. So we end up with the ions being pushed out over here, and we have some of the positive ions. We have some of the positive ions that were in here end up getting pushed in as well. So the net effect is we moved negative charge to the right. So the net effect is a move of negative charge to the right. The magnitude of that potential difference is going to be a function of the zeta potential of the capillary and the pressure difference. It's directly proportional to those. It's inversely proportional to the viscosity, because the greater the viscosity, the less flow we get for a given amount of pressure. It's also inversely proportional to the electrical conductivity. And so I'm going to use kappa sub E for electrical conductivity to distinguish that from the kappa. And we will annotate that to remind you that conductivity is going to be in Siemens per meter. Okay, so because we have this voltage difference, this excess of charge over here, there's a measurable potential difference, and indeed if voltmeter, we would see the needle deflect. Right? There's some non-zero voltage difference between those two ends. Let's see how big this effect is. So in this example, we have a capillary of a certain size, the zeta potential, and it's in a electrolyte solution, and we're going to pump liquid through it, and as a result we know there's going to be a potential difference between the two ends of the capillaries. So what is that potential difference? Before we start, we have to see what is the conductivity of a 1 millimolar sodium chloride solution. And values for conductivities of electrolyte solutions are tabulated, they're easy to find, and we find that 1 millimolar sodium chloride is going to be 0.012 Siemens per meter. So having looked that up, we can get ready to calculate our answer, and we should convert our pressure difference from bar to SI units, so that would be 10 to the 5th pascals. Okay, so let's plug all that in. We plug in the dielectrics, we plug in our zeta potential, plug in the viscosity, and our conductivity. Okay, and make sure that as an exercise you go through and verify that this ends up with units of volts. And that comes out to 0.52 volts, so definitely a measurable effect. Note the negative side of the potential. That means that there'll be a negative potential on the high pressure side of our apparatus, and that makes sense. We have a negative zeta potential on the walls of our capillary, which means that we're going to have an excess of positive charges in our capillary, and they're going to be pushed to the low pressure side, leaving behind an excess of negative charge. So we're going to have a negative potential on our high pressure side of our apparatus, and that emerges naturally from the equation.